Okay, this is the second and final hour of Physics 1C for October 6th. We're going to be talking about magnetic forces now. So, magnetic forces could be the force between two magnets. But there's also a type of magnetic force that's felt by electric charges. And I'm going to kind of tell you some of the properties of this force before I describe what it is. So, what we know is that if I have a magnet or a magnetic field of some kind, so let's say we have a magnet here, and we label one to the magnet as north, and we label the other to the magnet as south. One thing we know is that if you were to place a positively charged particle near this magnet, like right here, if that particle is at rest, so if it has no velocity, so we just take a charged particle and we say that it's at rest, or it could be a charged sphere or a charged balloon. So you take a balloon, you rub it on your shirt, you get some charges on it, you put it up next to a magnet, you want to see, okay, does the magnet affect it? You're going to find out that it's really not going to affect it very much. So what we know is that this particle feels no force in this case. The next thing we can say is that if I take a charged particle and I make it move near the magnet, all of a sudden there is going to be a force. Okay, so the next scenario would be, suppose that I have some magnetic field. Let's see, what's the best way to do this? Let's say I have a magnetic field that points like this. Okay, so I'm going to introduce a notation here that we're going to use pretty consistently in this class. I'm going to use this symbol to represent a vector that points out of the page, okay? Or out of the screen. And then I'm going to use this symbol, either with a circle around it or not, to represent a vector that points away from you. This would be like out of board or out of screen. This would represent into the screen or into the board. So let's say that I have a magnetic field, and I'm going to tell you right now that this is the symbol that we use for magnetic field, B. And let's say that it's represented by those arrows right there, okay? And it points into the screen. You might ask, well, how do I produce a magnetic field that looks like this? Well, one way that you could do it would be to do something like this. Imagine that we take a magnet and we orient it like this. We take the north end of a magnet right here, so that the south end is way up here. And very, very near to it on the bottom, I place the south end of a magnet right here, but I fix the magnets in place so that they can't move. I clamp them down or whatever I do. What I would say is that the magnetic field between these two objects is going to point like this, from north to south, and it's going to become very straight, kind of similar to a capacitor, but for a magnetic field. And the symbol that we use for magnetic fields is B. Okay? So imagine that above my screen, I have the north end of a magnet kind of right here, and then behind my screen, I have the south end of a magnet. Then I'm going to get a magnetic field that points into the page like this. Does that make sense? So, given a magnetic field like this, I just said that if I take a charged particle and I put it at rest near this magnetic field, it's going to feel no force. However, if I take a charged particle, yep, that's right, Ash. It extends everywhere. Yep. And I'm really just showing the region kind of just in between these 2 points, basically, in this picture here. Because there would also be, well, we can go back just a little bit here, right here. So can you see right in that region right there? I can blow this up just a little bit here. That the magnetic field's very straight there. That's the part we're talking about. And the closer together these two things would get it, they'd be straighter. But of course, it would still be curvy too. We're just looking at the straight region. So if I have a positively charged particle and it has a charge Q, so I've got a positively charged particle right here, if that charged particle is to move in the magnetic field, so if it has, let's say, a velocity that points off in this direction, okay, not a voltage, but a velocity now. I've got a charged particle and it's moving near the magnetic field. What experiments show us is that this charged particle is going to feel a force that's going to point up in this direction here. Let's use a different color for the force, actually. Let's use green. The force on the particle is going to point straight up in this case. And all three of these vectors are going to be at right angles to each other. The velocity vector, the force vector, and then the magnetic field vector, which points into the board. And they're all vectors, too. I should really identify that the magnetic force is a vector. So FB stands for magnetic force. Velocity is a vector, of course, that you've learned about in your Physics 1A classes. And then magnetic field is also a vector, just like the electric field is. All three of them are vectors. And in this particular case, if I have a charged particle and it moves to the right, it's going to feel a magnetic force that points up, just like that. It's a positively charged particle, though, so it would be reasonable to ask, if I replaced it with a negatively charged particle, what would happen to the force? And if you were to guess that the force would point in the opposite direction, you'd be right. So the negatively charged particle feels a force in this case that would point down if it's also moving to the right. So let's go ahead and throw that on the picture here too. So if we take a negatively charged particle, let's say that we represent that by a blue color. If it's also pointing to the right, then that same particle is going to feel a downward magnetic force. Okay. There's a couple things we can say about the force that this particle feels. The size of the force is going to be proportional to the size of the particle's charge. So the bigger the charge is, the bigger the force is going to be. It's also the case the bigger the magnetic field and the bigger the velocity will all affect the size of that force. So in general, what we can say is the size of this force, the magnetic force that acts on these particles, is proportional to three different things. It's proportional to the charge, it's proportional to the velocity, and it's proportional to the magnetic field itself. All right? The bigger the charge, the bigger the force, the bigger the velocity, the bigger the force. Pretty simple, right? The bigger that these things are, the bigger the force that it's going to experience. When the velocity is 0, there is no force. When the charge is 0, there is no force. When the magnetic field is 0, there is no force. You have to have all three of these things together. The particle must have a charge, it must be moving, and there must be some magnetic field. Otherwise, this force will not happen. And this is what we call the magnetic force. And we often use the symbol F with a little B underneath it to represent magnetic. This B is what we're going to be using to indicate magnetism. I don't remember why it's called B. I know Maxwell used D and H. Or just H. Maybe H and B. But I don't remember where the B comes from. There is a vector that we use M for. And it's related to like magnetization or something like that, I think. But I don't remember off the top of my head what it is. Is that it? Is that the general idea? Is that I told you everything you need to know? There's one other thing you need to know. The other thing you need to know is that I oriented this intentionally so that the charged particle was moving in a direction that was perpendicular to my field. The magnetic field's pointing into the board, indicated by these X's, and the charged particle was moving with a velocity vector like this. So suppose that I give you a slightly different scenario. If I have a magnetic field, and let's say that it points this way, so that's my magnetic field. Hey, you're right, Mr. Meowers. The right-hand rule does work out there, doesn't it? If you do V cross B, it tells you the direction of F, right? And we'll talk about that next. But for now, I'm just introducing like what's going on. Now, if I have a magnetic field, and what color was this before? Was it black? Yeah. Okay. If I have a magnetic field, and now I put a charged particle inside of here, but I make it so that the charged particle moves parallel to the magnetic fields. So if this is the velocity vector, this particle is not going to feel any force at all. Oops. The force on this particle is going to be 0. Okay, so if the charged particle moves parallel to the fields, or anti-parallel to the fields, if it was moving this way, the other way, it would also have no force, then you're going to get 0 force, okay? So there's something else we need to include in here, which is something about the angle. Okay, and it's not going to be directly related to all of these over here, but we know that the angle is going to have an effect somehow on what's going on here. And what we'll find out is that the force is going to be maximum when the angle between the velocity and the magnetic field is 90 degrees, and the force is going to be 0 whenever the angle between them is 0. So really what's going to happen is it's going to be related to the sine of the angle. Okay? Do I want to show you so we can put all these things together here, and in general what we're going to find is that the magnetic force in terms of its magnitude is going to be related to something like the charge times the velocity times the size of the magnetic fields, and then also multiplied by the sine of the angle between the velocity vector and the magnetic field vector. Okay? And these will all be magnitudes in this case. The more general form that we can produce for this uses the cross product. The magnetic force is equal to the charge on the particle. You include the sign of the particle's charge, and then you take the velocity vector, you take the cross product of that with the magnetic field vector. This requires that we have a little review of what the cross product is, so I'll talk about that in a second. But for now, I think what I want to do is, I think we have enough to watch one of these videos. Not this one, not this one. This is the one we want to watch. So to do this, I need to share my screen again, or at least to change it. It shouldn't... Can you tell me really quickly if you can hear this? There's no sound. To answer your question, it's Q times V cross B. In fact, I'll go ahead and grab this thing right here. That's it right there. Charge, velocity, magnetic field, cross product. We'll come back and we'll talk about that in a second. Oh, you can't see it. We'll get back to that. Let's go back to the video right here. I think you should be able to hear this. Tell me if you can't hear it. You can see the video, right? Okay, can you hear him? Okay, great. All right. Like, a very short video. We're going to watch this. It's a nice little demo. Okay, what do you guys think about that? Do you have any questions? We're going to go into more detail about, using the right-hand rule. It's really neat though, right? It kind of looks like magic. If you remember in any way, this little tube here at the front, I don't know how many of you guys have even seen this before, but about 20 years ago or so, the most common types of monitors that you would find in a computer laboratory would have a face that looks kind of like this, like quite literally a big tube. I don't know. So when he called this a cathode ray tube, that's CRT. And I know someone mentioned earlier that people use these still for older video games like Smash Brothers competitions and stuff like that. But the principle of what's happening here, of deflecting this beam right here, is literally how older images were produced on screens. Nowadays we use LCDs, QLEDs, LEDs, all kinds of different types of monitors that we're using these days that are, a little bit nicer. But this is how we used to produce images. There would quite literally inside of these old TVs be this little magnet, and it would cause beams of electrons to scan across and produce images on the screen. So, but for now, we're just interested in the fact that when you bring the magnet nearby, it takes this beam of electrons and deflects them downwards like this. Okay, so we can see the properties. Before we go into talking about the right-hand rule, let's just talk about the cross product itself. Let's make sure that we have a brief summary of what the cross product is. So the cross product is one of the two types of vector products. Oh, thank you. Okay. So back here, we want to talk in general about what the cross product is, just to have a kind of quick reminder of what it is. The cross product is one of two types of products that we have in physics. What's the other one called? So we can distinguish the two of them. The dot product, right? So in general, they work off the principle that, or the inner product as well. That's how you can, one other name you can give for it. So let's use one of our shapes here, because I kind of need to have 3 dimensions for this. All right, so we got an x, y, and a z axis here, right? And what I'm going to do is I'm going to draw a vector that points along the x-axis, like this, and we're going to call that vector A. And then I'm going to draw another vector, and I want you to just imagine... No, actually, let's just be simple with this. Let's draw another vector, but let's put it on the y-axis, like this right here. And we'll call the angle between the two of them phi. You can see that it's 90 degrees, but that's more for just demonstration purposes. The way that the cross product between two vectors is defined, A cross B, is that it's equal to the magnitude of one vector multiplied by the magnitude of the other vector, which I indicate by just not putting the symbol. This just means magnitude. And you multiply by the sine of the angle between the two of them. But this doesn't tell us the whole story. This only really tells us what the magnitude of the vector itself is. There's a direction associated with the cross product, because what the cross product does is it takes two vectors, and when you multiply them, it outputs a third vector. And in this case, the direction is given by what's known as the right-hand rule. It's defined that way because it's related to your right hand. The way that the right-hand rule works, and this is kind of difficult to describe without using video, and I could turn my video on here, I guess. But showing it to you guys... Wait, I'm just sharing screen, right? So I could turn on my video, I guess. It's kind of dark in my house right now. So what the right-hand rule tells us, and I've got... Well, it tells us that if you point the fingers of your right hand along A, and you rotate them up towards B, your thumb points in the direction of the vector itself. Can you guys try to do that for me? Can you take the fingers of your right hand and point them in the direction of vector A, so to the right, and then you curl it towards B. That's right. So you take the fingers of your right hand, you point them in the direction of A, and you curl towards B through the shortest possible angle. What direction does your thumb point if you do that? Can you answer in the chat? Yeah, it hurts my hand too, dude. It really hurts my hand as well. out of the page. So I want everyone to be able to try to do that. I'm sure a lot of you guys are not at your screens right now, but if you're at your screen, point your fingers in the direction of A. It definitely should hurt, because in order for me to point my fingers in the direction of A, it would almost be easier for me if I got up out of my seat, I believe. Yeah, it's a lot easier for me if I stand up, and then I turn my body in the direction of A, point my hand out, and then rotate my fingers toward B. Your thumb should be pointing out of the page, and the way we can indicate that in this picture right here would be to draw a vector that would point this way. So along the z-axis would be the direction of A cross B. That's pretty much it. Palm up. Yes, Astro Lover. Point your fingers in the direction of A with your palm facing upwards, and then your thumb will automatically point in the direction that you need to go. That's the right-hand rule. That's pretty much it. So there's some properties for the right-hand rule, which are that if we do B cross A, this is always going to be equal to the negative of A cross B. So it's anti-commutative. If you change the order, then you get a negative sign. And okay, let's look at some pictures here to try to get a handle on this. So this little diagram right here is kind of more about just the features of the magnetic field and the force. I think I've already described all these ideas here, so I'll just leave this in these notes off to the left here. But what I want to grab is... Oh, did I not include it? I know I did, because it's this huge picture. 1 second. Nope. Where did it go? Oh, there it is, right there. Okay. All right. This is a lot of information I'm throwing at you here, but I think it's going to do a better job than me just talking. So we'll just go through this really slowly. Okay, this is the right-hand rule for the direction of the magnetic force on a positive charge moving in a magnetic field. Okay? So you place the V and B vectors tail to tail. Okay? So if V is going this way, B is going this way, put them tail to tail. You imagine turning the vector V towards B in the VB plane. So the vectors V and B are always going to create a plane. And you basically, you try this with this one. You'd point your fingers in the direction of V, off this way. You'd rotate the fingers of your right hand towards B. So for velocity to magnetic fields, and your thumb should point up. Are you guys able to verify that in this case? That your thumb would end up pointing up? Okay. The force acts along a line perpendicular to the VB plane. You curl the fingers of your right hand around this line in the same direction you've rotated V. Your thumb now points downwards. So in this picture, the velocity vector points off that way, and you should be able to show that if you point your fingers in that direction, this should hurt your hand a lot less, and rotate towards B, that you get your thumb pointing downwards, like this right here. What we saw in the video was a stream of negatively charged particles, and he showed that the right-hand rule basically gave you the wrong answer. And that's why, if the charge is negative, the direction of the force is opposite, and you have to flip it around. So you do the V cross B part. Notice that these two pictures are exactly the same. The only difference is this is positive, and this is negative, and because it's negative, the force goes down. And that's it. That's the right-hand rule. Anyone have any questions? We're going to do some exercises. And the goal will merely be to end of this chapter. Just get some understanding of what we just talked about, just to kind of verify that you can do this on your own. So we're going to go through a couple of these. There's that one there we're gonna look at, and then we're gonna look at these ones right here. Okay, so let's start off with just this one here. We have a positively charged particle. It's moving to the right, right? It encounters a region of space where you have a magnetic field. What direction is the field pointing with these X's? Do you remember? Into the screen. That's right. Okay. So what would the initial deflection direction of this particle be once it enters the magnetic field? It's going to come into the magnetic field here. is it going to deflect downwards, upwards, into the page, out of the page? Can you answer in the chat what you think it is? You can check it. If you don't know what it is, it's fine, but just like think about it. When it comes into this magnetic field right here, what direction does the force act? Yep, you're all saying up, and that's correct. If you point your fingers the direction that the velocity vector is, which would be kind of to the right, and then you point your palm into the page, your thumb should be pointing upwards, right? Curl your fingers, your thumb goes up. Okay. For the next one here, what I want to do is I want you to think about this one. Yeah. I want you to think about this one, but I don't want you to put your answers immediately. So, okay, there we go. I just want to make it fill the screen. So for all of these pictures right here, we just did this one, right? Okay. What I would like for you to do is to just, you can either write down at your desk if you don't feel comfortable typing into the chat, or start to type into the chat. What I want you to do is to put your answer for what direction the force is going to be in each of these 4 cases, but I don't want you to answer anything until I ask for it, okay? So don't type anything in the chat until and so for this one, you'd say A is up, right? So I want you to just write A up, B whatever, C whatever, D whatever. Type it all out in one string, and then don't push enter in the chat until I ask for it, okay? I'll give you guys a couple minutes to try to do this. If you want to just write it down on a piece of paper, that's fine too, but just try to do it. Getting it right, getting it wrong isn't what's important here, okay? I believe it's Shift-Enter, Ash. You can test it. I might be wrong. So go ahead. I'm going to give you guys 2 minutes. At 8:27, I'm going to ask everyone to, enter their answers, and we'll see how everyone does. This is not about getting it right. It's about trying. If you don't understand how to do this yet, that's fine. Giving it some effort at all will help you to learn something. Okay, you can put your answers in now. Just looking for directions here. All right, let's see here. So A, the answer is definitely going to be up. For part B, you would go, you point your hands to the right. This was kind of hard because you got to like flip your hand upside down. And then you would rotate your fingers up. That would tell you that it would be into the page, but you got to flip it. It's actually out of the page. So the answer for part B is out. Do you understand? So B is out. Yeah, it's a negatively charged particle. What's the answer for this one? Did 0? Yep, a lot of people got that right. The answer for this one is 0. And then for this one, you point your fingers of your right hand upwards. You rotate them toward the magnetic field. This one's going to be into the page. So it was out of the page, 0, into the page, I believe. Right? So it's out, 0, into the page. All right. You have any questions? Does that all make sense? All right. So let's keep going. Let's do some mathematics with this, I suppose. There's gonna be 2 problems we're gonna do. We're gonna do this one. Oh, okay, we're just gonna do one actually, and then we'll talk about circular motion. All right, I think I'm just gonna let y'all do this problem yourselves, and just give you a minute or 2 to do it. So we'll read it though. We've got this picture. We've got a charged particle, a beam of protons, so that's their charge, moves at 3 times 10 to the 5th meters per second through a uniform 2 Tesla magnetic field directed along the positive z-axis, so the magnetic field points this way, through a uniform, the velocity of each proton lies in the xz plane and is directed at 30 degrees to the positive z-axis here. We want to find the force on the proton. We want to include the magnitude and direction. And for this, I'll write down the formula again. The formula was F equal to Q times V cross B. Or magnitude of the force is equal to QVB, sine of the angle. What would the force be equal to? So what's this equal to? Can we get an answer? Yep, 4.8 times 10 to the negative 14 newtons. That's right. And what direction does it point? Negative y or down, right? So we could write this in terms of a vector if we want to by using unit vectors. It would be 4.8 j hat negative. It's pretty simple. Anyone have any questions? Oh, whoops, not 19. All right, so that's pretty straightforward, right? So, next thing we want to do is we want to talk about the motion of a charged particle. Oh, we want to do magnetic field and flux. Okay, we've already talked about magnetic field, but we can talk about flux real quick. All right, so magnetic flux. So magnetic flux is similar to electric flux in the sense that it requires really just two things. You need, so we're going to use the symbol phi b for magnetic flux. We're going to say in general that if you have a flat magnetic field and it's uniform, and you have a surface that's somewhat uniform, magnetic flux is going to be defined as magnetic field dot product with area, which means that it's going to be equal to b times the area times the cosine of the angle between the two of them. And the way that would set up would be, suppose that I've got some magnetic field that points like this, and I have some area. The area could be drawn as some kind of a plane that could be coming kind of like out of the board towards us, so that we're looking kind of at the edge of it here. We define the surface of that plane to have an area vector, where the area vector points perpendicular to the surface, and the angle theta is the angle between the two of them, like that. And then we just define the magnetic flux that way. Magnetic flux is going to have units of Teslas times meters squared. I think that the name for this is a Weber or something like this. But in general, we can also define magnetic flux over curved surfaces. And that type of magnetic flux is defined very similar to the way that electric flux is, where you have to do an integral of b dot dA over the curved surface. This would be a non-uniform magnetic field or a non-uniform surface. And one other thing that we can state about magnetic flux is that if we do the magnetic flux over a curved surface, over a closed surface, so these are both surface integrals. If you do the magnetic flux over a closed surface, the answer that you're going to get is always going to be equal to 0. This is what's called Gauss's law for magnetism. What it says is that if I choose any closed surface around any magnetic field, it doesn't matter what the magnetic field is, that if I take the net flux through the surface, it's always going to be equal to 0. Why would that be the case? What was Gauss's law for electricity? It was, lines in equaled lines out. There you go. That's right, Tyler. That's exactly right. It's because the lines in always equal the lines out. With electric flux through a closed surface was always equal to what? Or proportional to what? The electric flux through a closed surface, it's proportional to the charge, right? And because there is no such thing as a magnetic charge, because there's no such thing as magnetic monopoles, this is always going to be equal to 0. And one way you can think about that is by looking at this picture right here. Can I copy this down here? Because it's related to magnetic field lines, I guess. We'll make it bigger. If we were to take on our picture right here, and we threw into it some type of a surface, what's going to show up here? Well, probably red. If I choose, nope, that's not going to work out. We're going to have to draw it over here, and then you know it's going to get covered up. So maybe you're just going to have to imagine this. Is it going to, no, it shows up. Okay. So if I take a surface, which we're just going to represent a cross-section of a surface here with this little circle. Basically, any line that comes in from the north side is also going to go back out to the south side. And it doesn't really matter where I put it either. If I put it right in between here, all the lines that come in from the front are going to go out to the other side. If I pick a position over here, any line that comes in this side also goes out the other side. So that's why we say that the net flux through any closed surface is equal to 0. And we call that Gauss's law for magnetism. Does that make sense? Okay. So that's magnetic flux. The other thing I want to say about magnetic flux is kind of just stay tuned. It will show up in the next chapter. It's going to be really important. For now, we're just defining what it is. Later on, we're going to find out that magnetic flux is inherently related to how magnetism and electricity are connected to each other. All right. So this will probably be the last topic because we're going to do 2 problems. We're going to talk about the motion of a charged particle inside of a magnetic field. The motion of a charged particle inside of a magnetic field. So let's say that I have a magnetic field, and I tell you that in some region of space, it's uniform, and it points into the board. So we have a magnetic field represented by these little arrows right here. All of them are pointing into the board in this region of space. And then I tell you that I have a positively charged particle, and let's say that it starts off at this location here. Let's move it over just a little bit. This part off right here. So this positively charged particle, let's say at some moment in time, is moving to the right with some velocity v. And we'll say it's positively charged and it has a charge q. So what's the direction of the magnetic force on this charged particle at this moment in time? Does it point left, up, down, right, into the board, out of the board? What's the direction of the magnetic force on this particle? It's not into the screen. It's up, yeah. Point your fingers in the direction of V, curl them towards the direction of the magnetic fields, and your thumb points up. Okay, so the magnetic field in this case is going to point, or sorry, magnetic force, excuse me, is going to point up like this. Now, what's that going to do to the particle? Does that mean the particle is going to start moving upwards, straight upwards? What's going to happen to it? It's going to curve, right? Exactly. So that's going to cause this particle to have this velocity vector tilted kind of up that way, right? That means that the path that the particle is going to travel on, let's just use purple for the path, it's probably going to travel on a path kind of like this, right? At which point, at this point right here, what would the direction of the force be? So after it's curved a little bit, and it gets to this point, like let's say right here, where its velocity vector goes that way, what's the direction of... the horizontal velocity stays the same. That's not true. The speed will stay the same, but the particle will curve a little bit. What's the direction of the force when it gets to here going to be? So it curves up a little bit due to that force. What's the direction of the force here going to be? Nope, it's not straight upwards. The velocity vector is now pointing this way. Yeah, as you can start to see, it's going to travel in a circle. But I just want to know, very simply, what direction is the force at this location? It's perpendicular to the velocity. That's right. And it's going to point kind of like that way, right? Up or left. Yeah, exactly. There you go. And if we trace this along, we'll find out that this particle eventually is going to be kind of like a quarter circle away right here. At which point, its velocity vector is going to point up. And if the velocity vector points up, well, now the force vector is going to point to the left, right? You can kind of get the idea that if you just point your fingers in the direction of the velocity in this case, and you punch your palm into the screen, that the force vector is always going to point up to the center, right? So as the particle curls the way that it's turning, if you follow along the path with your fingers, your thumb is always going to dictate the direction of the force, which is going to be into the middle. So the path this object is going to take, as you kind of predicted there, is going to travel along kind of a circular path. Oh god, this is awful. It's going to go in a circle, kind of like this. That's kind of okay. When it gets to the top right here, it's going to have a velocity vector that goes this way. And then when it gets here, it's going to have a velocity vector that way. When it gets here, it's going to have a velocity vector that way. And the force will always be towards the center in this case. God, that picture looks awful, but it's good enough. In this case, the force will always point toward the center of a circle. And I would say that the path the particle is going to travel on is going to have a radius r. The magnetic force is not going to change the speed of the particle. It's only going to alter the direction of the particle, because at every single point right here, it's always going to be pointing at right angles to the velocity. And if the force is at right angles to the velocity, it can't change the speed. It can only change the direction that it's traveling. So what happens here is that the magnetic force causes the particle to go into a circular motion pattern. The type of circular motion would be what we call uniform circular motion. Uniform circular motion is what happens when the magnitude of the speed doesn't change, right? So we get uniform circular motion, and in uniform circular motion, we can state that the net force that acts along the radial direction for our particle should be equal to the mass of the particle multiplied by its radial acceleration. And in this case, the radial acceleration is always going to be pointing towards the center, like this. And the value of that radial acceleration, do you guys remember from Physics 1A what it's equal to? Also known as centripetal acceleration. V squared divided by r. Yep, that's right. So if r is the radius of the path and v is your constant velocity, then the radial acceleration is v squared divided by r. On the left-hand side of the equation, we just have to put the force. In this case, that force is the magnetic force. But we know what the magnetic force is going to be in this case. The velocity vector is at a perfect right angle right here, which means the magnetic force is just going to be q times v times b, and then times the sine of the angle between the two of them, which at all points in this, between the velocity vector and the magnetic force, is always 90 degrees. Now, what we can do with this equation, well, we can notice that the velocity here and the velocity there show up. So we can drop a velocity, and if we want to, we can solve this for r. So we'll do that. What we end up getting is that the radius of the circular path is equal to m times the velocity divided by q multiplied by b. That's the radius of the circular path. This is a really handy relationship right here. It relates the radius that it's curving through here for the circle directly to kind of like its momentum, and then to these features related to the force, the charge, and the magnetic field. Kind of a nice little relationship. Something that, I don't know, I use this in the work I did to talk about like curved paths that particles would take. And we're going to get to that later. What kind of features does this tell us? It tells us the size of the radius is dependent on all these factors. The faster that the particle moves, the bigger the radius will be. Does that make sense? If it's got more velocity, does it seem reasonable that it would go a bigger circle? Right? It's kind of like it's got more of its own momentum. Bigger mass, same thing occurs. If the particle itself has a larger mass, it's going to have a larger circle. The bigger the charge, though, is going to make it have a tighter circle, because the bigger the charge, the bigger the force, right? And also the bigger the magnetic field, the tighter the circle is going to be, because, you know, for the same reason. But this is a really nice property by which we can effectively cause particles to move in circles just by the presence of a very large magnetic field. Anyone have any questions? So I'm just going to relate this to something that like is related to my own like area of like physics that I studied. So in particle physics, one of the things we did was we forced charged particles, in particular protons, to travel in really big circular paths, and in order to control their motion, we used magnetic fields just like this to force them to move along circular paths, and then we would force them to collide into each other. In addition, when we collide the particles together, and this is done, Okay, if you don't know about this or haven't heard of it before, currently at a place called the LHC. The LHC is something called the Large Hadron Collider. It is a large circular collider shown in this picture here, drawn on a map. This has another collider that's being built, but it's a 27-kilometer ring right here that has other tiny rings. I don't know how well that's showing up on your screen. There's other tiny rings that are like little accelerator rings. They inject particles traveling in one direction here and the other direction there, and then they collide with each other somewhere along the ring. They call it an atom smasher because we're literally smashing together little protons, and when you smash them together, little pieces come out. When we observe the pieces that come out of them, we use a detector. This is the detector right here. It's looks like something out of a science fiction movie. This is a better version of it, actually. You can see how big it is, by the way. So there's a large magnet here, and it has the effect that when the collisions occur, the particles get just kind of broken up into tiny particles, and then they just spew out, okay? And the kind of stuff that we end up observing in the laboratory, this is a pretty good picture, actually. Is it, though? I don't know how big this one is, so I can show you. Let's see how good this picture looks. Oh, page not found. That's unfortunate. Let me find one of these pictures that I can show you here that looks kind of better. Some of these are a little more three-dimensional than I would like. This one's pretty good. Here we go. So, oh no, what did this just download? I don't want to know. Okay, whatever. I probably have a virus now. Okay, what is all this junk? Oh my god. Okay, whatever. Let's go back. What, can it just let me look at the image, maybe? Open image in detail. Let's try that. All right, there you go. Take that, ad blocker. And now it's all fuzzy, but every single one of the things in this picture is a particle. Like, every one of these lines is a particle. Do you see how they're all curvy? All the lines? Can you guys tell that from this picture? I really should have gotten a picture ready before class. I didn't think I was going to talk about this. Okay, another thing to notice here. Some of them curve this way, and some of them curve that way, right? Can anyone guess? Why do some of them curve this way, and some of them curve that way? And I'll tell you, the magnetic field is pointing into the page. Like, they're opposite in charge, yeah. You could say some of them might be electrons and some of them might be protons, Ash, but it turns out that they're actually either electrons or even more fundamental particles, as it turns out. But yeah, there's other things that have positive charges. So there's several things that you can do with this. The curvature of the track, right? Okay, we just learned about this. The curvature of the path is given by this right here. So by measuring the kind of the radius of curvature, as we call it, you get a direct measurement for the mass of the particle, the charge of the particle, and the velocity of the particle. The magnetic field is fixed. Whether the charge is positive or negative, you can tell from the picture if it's positive or negative because some of them go left and some of them go right. And if they have a really big radius to their circle, well, that means that the mass times velocity, or the momentum, right? We can write this even more simply because, honestly, in these type of collisions, often we really just care about the momentum. This really just says it's the momentum divided by q times b, right? So you get a direct ratio from that radius of the momentum over the q, and then if you could alternatively measure the momentum, which we do with other types of devices in the system, by measuring how quickly the particle moves between like this point here and this point here, we can measure the momentum, and that allows us to exactly find the charge. It also allows us to exactly find the mass. So this is how we look for new particles. It's almost 100%, just this thing right here. This is the biggest part of it, is understanding the way in which the magnetic force of that, I'll show you again, the gigantic magnet, which, it's on the previous page. This big magnet, that thing right there, that gigantic magnet, which is this huge magnet that's causing these little particles that are moving really quick. In fact, the particles in this particular experiment are moving very close to the speed of light. Anyway, so that's the motion of a charged particle in a magnetic field. You guys have any questions? Yeah, I used to work at a place like that. The LHC is in Europe. I worked at a place in Chicago that's called Fermilab. That's where I worked. I worked there while I was in grad school. And I worked on one of these machines like this. I worked in a little control room that was kind of off to the side over here, where I would monitor some of the systems. In particular, I monitored something called the silicon microscope tracker system, which was used to be one of the first indicators when we were looking for particles and stuff like that. Do they only do one particle at a time? You mean during the collision? Yeah. Okay, so the way the collisions happen, they happen in bunches. So on the ring, where's the ring? Here's the ring. On this ring, it'll be, okay, so I don't actually know what the numbers are for the LHC, but the one I worked at, which was called Fermilab, I could pull a picture of Fermilab up, I guess, if you're, I don't know. Fermilab, or the Tevatron, has this very unique building right here, which I've seen shown up in some video games and stuff before. This is Fermilab. This is their big ring. It's not nearly as big. I think this one is, the other one was 27 kilometers around. I believe this one's like maybe 2 to 4 kilometers around. It's not big. I was able to ride my bike around it in a very short amount of time. There's like a track that runs around it. And at this one, to answer your question, when they would fire these things together, yeah, it has to be bunches of particles, Meowers. It's a huge number of particles that are colliding into each other at one point in time. And what they do is they kind of, the particles are moving in kind of a loose bunching, but then as they get closer to the impact point, they force all the particles to condense down. So imagine that it's like this big jumbly bunch of, I guess I could draw it. Imagine that you've got these two particles and they're going to be colliding in your ring. Okay, so here's your ring, right? And let's say you want to make them collide. This is your point when you want to collide right now. How do you know you want to collide right there? Well, wherever you want the collision to occur, you need to have your big gigantic detector, okay? So here's the point on the ring where there's a detector, okay? The detector I was working on, there's an O, whatever. The detector I was working on was called D0. The way it would work is you'd have these bunches of particles come in, okay? And you'd have big bunch of particles over here. These were all protons. Okay, and they'd be moving in this direction. They literally move with a velocity of, I don't know if this is going to mean anything to you, but I'm at least going to mention it. I believe it was 0.99995 the speed of light. That's how close to the speed of light these particles move, which is just insane. So we get them up to that speed, we bend them into a beam, and what was cool about the detector I was working on is it actually used antimatter. And so in this direction, we had a beam of what are called anti-protons. All right. Now, what would happen, and I don't remember how this happens. I don't remember what they do, but my guess is I think they use electric fields. I can't imagine what else they would do. I think they used electric fields, and what they would do is they would force these beams that would come in like thick. They would force them to come down to like a point. Like this, on both sides. So the beams come in, imagine it's like a nozzle, right? It's kind of like what it is. They come in like all spread out, being controlled by magnetic fields, and almost like a nozzle, you force them to impact at this point right here, and this is where you have your big explosion. Okay, and then the particles stream out like that. What's cool is literally anything that is less than the energy of the collider can be produced in these collisions. And the one that I worked at in 1995, it discovered the top quark. In the 2000s, it discovered the tau neutrino. The one at the LHC discovered the Higgs boson. It was one of the things I was working on, trying to find it, the one we were working on, but we didn't have enough energy to make it. But the Fermilab one had protons and antiprotons. The LHC just uses protons and protons. The antiprotons are harder to produce, so in your bunchings here, you would have much less antiprotons than protons. I think by a factor of 100 or so. You could have millions of protons, but you might only have a few thousand antiprotons. And then, to specifically answer your question, Mr. Meowers, when these things would interact with each other, because it's a huge bunch, hitting a huge bunch over here, you would actually get tons of collisions per second. Does that make sense? Because like one of these would collide with one of these, but there's millions of these, right? So if there's thousands of these, you're going to be getting something like 1,000 collisions per second. Does that make sense? And it's quite literally so much data that's produced that all of it gets offloaded onto a computer, but there's so much data being produced so quickly that you can only select certain events. If you tried to record all the data that was there, you would just need just a gigantic room full of hard drives, and you'd fill it up so quickly with information that it would be very difficult to look for what you're looking for. So the computer systems themselves, literally within fractions of a second, like within microseconds, they will take the data that comes out of it, and they have rejection biases where they decide if the data is good, they're going to keep it. And by what's good? Good means there's an interesting event going on there, okay? There's something happening in this event that's like, oh, maybe this is something new. And if it's just boring, nothing happening in this event, they just toss it out. And the computer has to make those decisions in a second. And of course, the way that the computer makes those decisions are based on programmers. Ultimately, the only thing that you do when you're a physicist at these things is you just write programs. The programs are either designed to search for things like unknown particles, or they're designed to produce cuts on what you believe to be an interesting event. It's really fascinating. We could talk for hours about this. I don't want to. I want to do at least one problem before we stop class, but all related to this little equation right here, which is what I think is so cool about this, is that this entire facility, although it's a marvel of modern engineering in many ways, of accelerator physics, how you actually get these particles moving this fast, how do you control the beams, how do you make the detector, what does it detect, all these kinds of things. Ultimately, the physics behind it are almost completely described by this right here, and that's a pretty powerful equation right there because of it. Anyway, do the protons and antiprotons produce particles? You thought it was just gamma rays. Yeah, I think that's a good thing to think. So the particles and antiparticles, when they interact with each other, they do produce a lot of energy. The thing is that when they produce that energy, out of the energy they produce, new particles can kind of be formed. Does that make sense, Tyler? Because of E equals mc squared. So if you pump a lot of energy into one location, then out of that energy, all kinds of other stuff can come. And, the goal is to produce things we've never found before. One of the things these detectors are looking for, they're looking for dark matter. They're looking for evidence of physics we haven't seen before. They're looking for evidence of, if you can believe it, extra dimensions to the universe. That's one of the things they're looking for. I think that's really crazy. We're literally probing the dimensions of the universe. Is this how Iron Man created his heart? Probably. No, didn't he just use a nuclear device or something like that for his heart? I don't remember. I haven't seen the first Iron Man in a long time. It's a good movie. Anyway, so it looks similar to this. Well, could be. Could be. Yeah. I'll have to go back and watch it again, maybe, and I'll let you know if I can find it on. Maybe it's on Disney Plus. The Flash was created that way? Okay. All right, let's do one problem and then we'll stop. It isn't Disney Plus? Okay, I'll see if I can go rewatch Iron Man, or at least the beginning of it. That movie's been a while since it's been out. Not this one. Not this one. Okay, this one here. Well, let's talk about this one too. Oh, this part all along. All right. So let's do a real quick problem with this. Oh, and let me mention one other thing, because this is going to come up on your homework too. So this equation right here, we can rearrange it in the following sense. I can write it as QB divided by m is equal to the velocity divided by the radius. What do I get if I have a particle that moves in a circle and I take the velocity and I divide by the radius? What does that give me? It's not radial. If it was v squared, that would be radial acceleration. That's not quite what it is. It's something else. Do you guys remember this? Radial velocity. That's close. Angular velocity. That's right. This is what we call angular velocity. So if I take qb divided by m, this gives me the angular speed. That would be the angular speed in radians per second. I believe your book calls this the cyclotron frequency. Cyclotron frequency, I think. QB over m. And this is going to show up in some of your homework problems. It also can be determined in terms of the frequency f as well, because omega is equal to, I think, 2 pi times the frequency. Yeah. Right? Okay. That'll show up in some of your homework problems. If they ask about cyclotron frequency, this is what they're asking about. All right, so a proton moving perpendicular to a uniform magnetic field. A proton is moving in a circular orbit of radius 14 centimeters, so we know radius. In a uniform field, B is 0.35 Tesla. With a perpendicular to the velocity of the proton, find the speed of the proton. Okay. What we know here is that it's a proton. I don't know how well you guys can read this. Let me... Why can't I select it? Come on. Okay. It's a proton, which means we know what its mass is. You can look up the mass of a proton either in your textbook, if you have it, or you can just look it up on the internet. Protons are really tiny. That's what their mass is. And then we also know what their charge is. The charge of a proton is the same as the charge of an electron. It's 1.6 times 10 to the negative 19 coulombs. We're trying to find the speed. So we use our equation we just derived, r equal to mv divided by q times b. We solve for the velocity. The velocity is going to be q times b times the radius divided by the mass. Plug in all these numbers up here. B is 0.35. When we're done with this, I'll tell you what Tesla is. I forgot to do that today. Radius is 0.14. Divide by the mass. 10 to the negative 27. What's the velocity you get out of that? Does anyone know? I bought a new phone over the weekend. I just got like a really cheap phone off Amazon. Why does it keep telling me I need to do security updates? I've installed like 9 different security updates. What's up with that? Is that normal? Also, it's Android. Also, the instructions for the updates are all in Spanish. I don't know why that is either. Everything else in the phone's in English, but the instructions are in Spanish. Not quite sure what's going on with that. I got 4.7 times 10 to the 6th. Does that sound about right? Okay. Yeah, it could just be that... I don't know. What is it telling me? Oh, no, I don't see it. I only saw it on the lock screen. Oh, whatever. Okay, let's talk about the unit Tesla, because I didn't mention that. So what is 1 Tesla equal to? So to figure out that, as usual, we use the equations we have and we relate it to the other variables we have. So for Tesla, what you want to use is this equation, QVB equal to the force. So Tesla, if we solve for that, B is equal to force divided by Q times V. The units for force are newtons. The units for charge are coulombs, and the units for velocity are meters per second. But then coulombs per second is an amp. So 1 Tesla is equal to a newton divided by a meter times an amp. It's a newton per amp meter. There you go. I think that's a good place to stop for today. We covered a decent amount of this chapter, and hopefully we can finish the rest of it next time.